So in previous yes, we were using the Laplace. We're taking Laplace transform of the derivative. All right. Now we're going to do the opposite. We're going to find derivatives of transforms. Later, we're going to find transforms of integrals, which we haven't done. And then we're going to do the reverse, find integral of transforms. And we're going to wrap up with the transform of a periodic function. These are very important, especially for you in engineering. Most of you are engineer where you work with periodic functions, whether in civil engineering or in an electrical engineering most commonly, you know. Let's see. So derivatives of transform is essentially multiplication by a power of n. So the Laplace transform of the product of a function f of t with t can be found by differentiating the Laplace transform of t. Okay, so to motivate this result, let's assume that the Laplace transform of f of t is simply f of s. I mean, that's what we have been doing. Nothing crazy, right? You didn't see us. It is possible to change the order of differentiation and integration. What do we mean by that? Because, okay, now I'm going to take the derivative, okay, of the transform. All right. I'm going to take the derivative of the transform. This is the same as saying the derivative of the Laplace transform of f of t. All right. Well, by definition, ds, that's the integral from 0 to infinity of e to the negative st, f of t, dt. Okay? Again, back to the original definition, the integral definition of the Laplace transform. But, okay, guys, but here, how are we going to differentiate this? Are we going to differentiate with respect s or are we going to differentiate with respect y? Well, in this case, it's with respect s because we are differentiating already the transform, which is already a function of s, all right? Let me introduce this derivative operator into the integrand. Now, here is the thing, guys. This is equal to 0 to infinity, integral from 0 to infinity of the partial derivative with respect s of e to the negative st, f of t, what is that? dt. Okay? Now, what I did here, it's what we usually call differentiation under the integral sign. That's a process you get to see in upper levels of mathematics. It's called Leibniz rule of differentiation under the integral sign. And this differentiation becomes a partial differentiation because what do we have? Two variables. We're differentiating this with respect s. Well, t is the constant, so we're going to get the partial derivative of the exponential, which is itself the exponential. Okay. Uh, that is the integral from 0 to infinity of negative, because the exponential is negative, e to the negative st times t, f of t, dt. All right? So what is this really equal to? This is negative the Laplace transform of t, f of t. Okay? I'm going to do this somewhat again. I mean, not the whole thing. So that means, okay, this means that the Laplace transform of a multiplication of a function by a power of t, in this case, a first power of t. We're going to get higher powers later. That is negative the derivative with respect x of whatever Laplace transform of some function we get, right? Whatever function of s, function of t, find it function of s and differentiate it and then multiply by negative one. We're going to talk about the negative in a second. Okay. Now, what about it? So here we can use the same idea to find the Laplace transform of a function multiplied by second power of t, by a quadratic power of t. That is the Laplace transform of t squared f of t Okay, this would be essentially the Laplace transform of t times t, isn't it? F of t. Okay, but hey, didn't we already find the Laplace transform for one power? This would be negative DDS. Okay, negative DDS. What is that? Negative DDS of the Laplace transform of t, f of t. So what did I do? I got rid of one power of t by differentiating, and we are going to be remaining with one power, right? And then what's the transform of, wait, the Laplace transform, we still need the Laplace transform here. This would be negative DDS times another negative DDS of the Laplace transform of some function of t, all right? Negative negative equals to positive. The derivative of the derivative, isn't that the second derivative? Okay, so in okay, what we were trying to say here is depend the number or the power of t, it's going to tell us how many times, oh, this is squared, second derivative. Okay, the power t is going to tell us how many times do we differentiate the transform. And also notice the alternation of the sign. While we had a negative for the first derivative, the second derivative is positive. The result is summarized here in the theorem below. If f of s is the Laplace transform of f of t, well, multiplication by a power of t, an n power of t is negative 1 to the n, which is the order, which is the power of n, that's going to be times d n ds to the n, which is the order of the derivative on the function that we're going to transform. Well, let's have a look at one example to see this result a lot better. Okay, so find the transform of t cosine 3t. Okay, so what are we going to do here? Because what's n number one? Okay, so number one, let's have a list of let's list our information. N equals to 1, that's the power of t, and f of t equals to cosine 3t. Okay, so that means we're going to do negative 1 to the first power d1 over ds1, that is essentially the first derivative, okay, of the function f of s. What is the transform? Let me do the Laplace transform of cosine 3t, okay? That is negative the derivative with respect s of the transform of cosine, isn't that s in the numerator over s squared plus the coefficient of t quantity squared, which is 9. Okay, so guys, we need to differentiate this. What rule do we use to differentiate that one? Quotient rule. Okay, so keep the sign negative for the very end. Okay, derivative of s equals to 1 divided by s squared plus 9 minus derivative of the denominator, which is 2s times the numerator s, everything divided by s squared plus 9. Okay, let's simplify all this madness here. Okay, number one, save the negative for the very end. S squared plus 9 minus 2s squared divided by s squared plus 9. There's not much to simplify here. I mean, we end up with this is equal to negative s squared minus 2 s squared, that's 9 minus 2 9 minus s squared over s squared plus 9, and we can use the negative to reverse the order of the terms in the numerator, that is s squared minus 9 divided by s squared plus 9. Yes, you're right. I forgot to square the denominator. Thank you. Yes, squared. And that's what I had in my notes, but I didn't see it. Thank you. All right. So that's one example. Let's do another example. One in which we're going to do the second derivative, not just the first derivative, just so you can see how that actually goes. Okay. So find the transform of t squared sine of 4t. All right. So number one, in this case, n equals to 2, and f of t equals to, what is that? Sine 4t. Okay? Sine 4t. So this will be negative 1 to the second power, the second derivative with respect s of the Laplace transform of sine 4t. And well, what's a transform of sine? Well, number one, negative 1 squared, that's going to be positive this time. And then we're just going to write the second derivative, indicate the second derivative. So is this, what was that? 16? Oh, actually, no, not 16. It's just, is it just 4, right? 4 over s squared plus 16. Is that the transform for the sine function? It's k, the number that multiplies the t inside of the angle, divided by s squared plus k squared. Yes, that's what it is. Well, guys, we need to differentiate this twice. Let's differentiate one time first. What rule do we use to differentiate? Hmm? Now, that's an integral. That'll be the. We're gonna do that later anyway. We're gonna do that later. Save that for later, right? Yes. What rule do we use to differentiate that one? Hmm? Chain rule? Why not the quotient rule? Well, not the quotient rule because the numerator is just a constant. So d squared, ds squared. I'm going to write this so that we can do some chain rule. All right? Do not do an unnecessary quotient rule here. Okay? So this will be equal to, okay, now that we're going to do a derivative, we have two derivatives. Now I'm already doing one, so that's a negative 1 times 4, which is negative 4 times s squared plus 16 times 2s, okay, to the negative 2, the parentheses. Well, let me rewrite this again in a nicer way. Let me take the negative outside of, and actually, what is that going to be? So 4 times 2, which is 8, times the negative, I'm going to take the negative 8 outside. DDS, and I'm going to write s over s squared plus 16 quantity squared. Okay? So now we're going to differentiate this beast right here. Well, that's going to be another quotient rule like before, all right? Because we have the variable s in both the numerator and the denominator. Okay? So this is equal to negative 8. No more derivative symbol because I'm already doing the derivative. The derivative of s, which is 1 times the denominator, s squared plus 16 quantity squared minus the derivative of the denominator. Be careful, it will require another chain rule. So 2 times s squared plus 16. 2 minus 1 is just 1 times by chain rule, that's 2s. But that's just the derivative of the denominator. We still need to multiply by the numerator, which is s. Okay? And then divide everything by s squared plus 16. But it used to be squared. Square it again because of the quotient rule. That'll be to the fourth power. All right? That equals negative 8 times, well, s squared plus 16 quantity squared. And then what is that? Minus 4? Minus 4 times s squared times s squared plus 16. Everything divided by s squared plus 16 to the fourth power. Okay, guys, I know what you might be thinking. Distributing the negative 4s squared and then getting a quartic polynomial, that's not going to take us anywhere. No. Check this out. I'm going to factor s squared plus 16. I'm going to factor actually 1 power of it because we have quadratic in the first term and just to the first power in the second. So I'm going to factor it out. And this will be negative 8 times s squared plus 16 to the first power, actually curly braces. Bracket, okay, we're left with one power that is s squared plus 16 minus 4s squared, okay? Well, divided by s squared plus 16 to the fourth power, okay? Let me make this a little smaller. So, what do we do next? Well, the purpose here is to divide out some factors. S squared plus 16, that leaves us with three of them, right? And then, combining like terms, I think I'm going to write that negative 8 in the numerator, negative 8, parentheses, s squared minus 4s squared, is that negative 3s squared? And 16 in the front, and divide that by s squared plus 16 quantity cubed. Okay, there's not much more to do other than maybe using that negative sign to reverse the order of the term. So that is, and you don't need to actually distribute the egg, that's fine, leave it in factor form. 8 times 3s squared minus 16, everything divided by, what is that, s squared plus 16 cubed. Final answer. All right. Final answer. Okay. Let's have a look at the next topic. Okay, what about the inverse form of what we just did here? Okay. So what are we going to do? So we're going to find the inverse transform of some function of it, right? Well, because what did we do to find derivatives of transform? Didn't we multiply by powers of t? Well, the inverse of multiplication by t is going to be to divide by t. So 1 over t times the inverse transform of negative the derivative of f of s. All right, we're still going to differentiate, but you'll see what we're going to do here. Okay, so let's evaluate each of the following. The inverse transform of natural log of s squared minus 4 divided by s squared plus 7. Well, this is the first time we get to see transforms of, well, to see the natural log function involved in a transform or an even transform. We didn't do that before. We're going to do that finally. Okay, guys. So there's no formula that gives us back some function in if we find the inverse function, the inverse transform of some logarithm. We don't have any. However, it requires a little trick here, which is using the inverse form of the derivative of a transform. So this is what we're going to do. We're going to multiply by 1 over t, and then we're going to take the inverse transform of negative, well, the derivative with respect s, okay, of all this madness here, okay, of this function of s, ln of s squared minus 4 over s squared plus 7. And guys, you don't want to differentiate this natural log of a quotient. 1 over the quotient times the derivative of the quotient? Hell no. You guys know about properties of logarithm, don't you? Okay, so this is what we're going to do. Okay, actually, for our convenience, I'm going to take this negative sign outside. That is negative 1 over t inverse transform of, oh, come on, the derivative with respect s of ln of s squared minus 4, right, minus ln of s squared plus 7. Can we make some room? Maybe make this smaller. Okay, close parentheses, close the bracket, close the curly braces. All right. Okay, what's the derivative of that natural log? I mean, number one, negative 1 over t, okay, negative 1 over t, inverse transform of ln of, that is 2s over s squared minus 4, right? and then minus 2s over s squared plus 7. Okay? Are those the transforms? I mean, the derivatives of those logarithmic functions? Okay, guys. Let's find the inverse transforms of these two. Did you recognize those two forms? Well, it's actually going to give us the same function in the world of t. Back in the world of t, isn't it? So, what function? What's the inverse of those? What function is involved? Hmm? What's the result right away? Just give me what function is involved back in the world of t, the inverse of these two. Cosine, all right? So in this case, this would be negative 1 over t times uh, cosine of 4t, no, rather 2t in this case, right? And no, actually, no, that's not cosine. That's actually cosh, right? Cosh of 2t, okay, the square root of this number. And that's actually 2 times, right? 2 times. And what else? Minus cosine square root of 7t. Okay. And we also don't forget the 2, right? Don't forget the 2. Okay. And finally, simply we do negative 2 cos 2t minus 2 cosine root of 7t, everything divided by t. All right. But now our final result is a division by t as opposed to finding the transform of a multiplication by t. All right. Okay, the next one. Yes, we're gonna have enough time for the next one, which is gonna be quite long, right? Yeah, so okay, so minus minus. Actually, okay, let me go back. There's a mistake here. This is supposed to be plus. Thank you, thank you. Okay. All right. Well, what about the inverse transform of s squared plus 1 divided by s squared? Okay, let's see about this one. Okay, so number one. By the theorem again, we're going to multiply 1 over t and then find the inverse of the opposite in sign of the derivative of that function we're given to find the inverse of. Okay? So let's see. So that is 1 over t inverse transform of negative dds of, in this case, s ln of s squared plus 1 over s squared. Okay? All right. So actually, to differentiate that function, we would need the product rule, don't we? However, okay, let me actually use properties of logarithms, maybe. No, maybe not. Maybe not. Okay, this is what I'm going to do. This will be, you, so this will be equal to 1 over t, okay, inverse transform of negative dds of the derivative. Oh, wait, no, no more dds. Actually, let me take the negative outside and simply differentiate the derivative of s, which is 1 times ln of s squared plus 1 over s squared plus the derivative plus s times the derivative with respect s of ln of s squared plus 1 over s squared. All right. Okay, what are we gonna do now? So, well, let me keep making more room. Otherwise, I may. Okay. So, I mean, ln of s squared plus 1 over s squared. Well, we're done with that one. Okay, so let's find. Well, not yet. We're not done yet. Hold on. We're not done yet. So, sdds, ln. Well, how about before differentiating this guy, we use properties of logarithms. Okay, so that is 1 over t So that equals 1 over t, or actually negative 1 over t, inverse transform of ln of s squared plus 1 over s squared plus s times dds. Okay, I'm not going to differentiate yet. First, I'm going to use properties of logarithms. That is, we're going to use actually two rules. The quotient rule of logarithms, that is ln of s squared plus 1 minus ln of s squared. But at the same time, I'm going to do the smackdown rule. Remember? Minus s, or no, minus 2 ln of s. Okay? And I'm going to close the curly braces. Okay, so guys, what did I do here? So number one, quotient rule. Okay, so this is ln of s squared plus 1 minus ln of s squared, and then smack down the power, ln of s squared plus 1 minus 2 ln of s. All right? Basic properties of logarithm. So let's differentiate and then see what happens. Okay? Now, negative 1 over t. Okay? Yeah, perfect. Inverse transform of, what is that? Uh, ln of s squared plus 1 over s squared plus s times the derivative of this. What's the derivative? S times 2s over s squared plus 1 minus 2 over s. Okay? You guys following me here? Okay, well, let's distribute that s. Let's distribute the s and see what happens. So distribute, okay? And that's going to leave us with negative 1 over t inverse of ln of s squared plus 1 over s squared plus 2s squared over s squared plus 1. But did you see how the s's cancel out here and leaving us with a plus 2? Okay, guys, here we have potentially a problem. We cannot take the inverse transform of just a number. Okay, and remember what was it? The transform of a number, that's the number divided by s. But we never look at the inverse transform of a number. So if you're doing anything like this and you get to this point, don't freak out. Yes, minus two. Yes, minus. You're right. You're right. Yeah, minus 2. Yeah. So what I'm gonna do here is divide by 1, multiply by s squared plus 1, divide by s squared plus 1, and combine fractions together. Okay, and this will be negative 1 over t. All right, negative 1 over t times the inverse transform of ln of s squared plus 1 over s squared. And this will be 2s, okay, that'll be minus 2s squared minus 2, everything divided by s squared plus 1. Simplifying the fractions together, what is that going to be? 1 over t, actually minus inverse transform of ln of s squared plus 1 over s squared. And what do we get here? Actually, this is supposed to be squared. Okay, so actually the 2s squared minus 2s squared, don't they cancel? And then minus times a minus, doesn't that become a plus? Plus 2 over s squared plus 1. Okay? Okay, let's have a look at the last term. Isn't that already this ready to find the inverse of to get the sine function? However, what about the first term? That first term still has a natural log term. So that means we need to do another iteration of this theorem, the 1 over t times negative dds, blah, blah, blah. I'm going to take a side trip just to deal with that one. Okay? So let me change color for such a side trip. Okay? Side trip. Okay. So I'm going to do the inverse transform with a different color of ln of s squared plus 1 over s squared. that equals 1 over t times the inverse transform of negative the derivative with respect s of ln of s squared plus 1. Well, actually, let me do ln of s squared plus 1 minus 2s minus 2 ln of s. Let me do, these properties of logarithms already. So we can differentiate at home and find the inverse transforms of those. So let me continue here. This is equal to the inverse transform of uh wait. I'm gonna take out the negative 1 over t inverse transform of uh 2s over s squared plus 1 minus 2 over s. Can we find the transforms of these two? Isn't that the cosine for the first term and the number 2 for the second term? You guys agree? So this will be negative 1 over t, okay? Negative 1 over t times uh, 2 sine of t minus 2, okay? 2 sine of t minus 2. So we could use that negative to reverse the order. That's negative 2 plus or 2 minus sine 2t, okay? Well, actually, no, it's cosine, right? It's cosine, not sine. It's cosine. It's a cosine function. Minus 2 cosine t, everything divided by t. So, guys, the inverse transform of this is going to be, what is that? Cosine t, right? And the inverse transform of this on the side trip is going to go to that, all right? Yes. So, so that's what we get out of the side trip and the inverse transform. However, there's a couple of sign issues. This plus, combining these two should remain plus and plus. Okay, that's the plus over there. And finally, we got negative 1 over t times the inverse transforms of these two, which is 2 minus 2 cosine t over t and cosine t. All right, which in this case is distribute the negative 1 over t. That is 2 minus 2 cosine t over t squared, actually negative, and then what was that, plus here, minus, because of the minus, cosine t over t. And you can leave it like this, or maybe combine the fractions together. All right. Uh-huh.